In our last video, we saw the formal definition of a limit. The limit is said to exist, or better said, the limit is x approaches c of f of x is L if, for every epsilon bigger than 0, there is always a corresponding number delta bigger than 0, so that if we keep the x's within delta of c, the y values will be within epsilon of L. Notice the 0 is less in here. What this is saying is that x is not allowed to be c. Well, if I look up here, that's the one place I don't care about, right? Except possibly at c itself. That's really why that 0 is down there. On the x-axis, I want to be close to c without actually getting there. Well, if x was equal to c, this absolute value statement would be equal to 0. So let's work an example where we actually have to process and understand the formal definition of limit. I thought we'd start with a linear function. Linear functions are great, easy examples. In fact, I bet we could even graph this very quickly without breaking a sweat. Nothing about the questions I have written here says, hey, graph this, but why not? Pictures are nice. My y-intercept's -2, and I have a slope of 3. Nice happy line. I know my x-intercept would be at 2/3. I have this picture here. I'm asked to evaluate this limit, and that's just what we've been doing, right? Linear functions are polynomials. I know I don't have to worry about any hop, skips, breaks, or jumps. They're continuous, and I get to just evaluate the function to find the limit. So 3 minus 2 is 1. All right, so I've satisfied the instructions there in part 1. The limit as x approaches 1 of 3x minus 2 is 1. Kind of a boring function. In number 2 here, I'm given a specific value of epsilon, and I'm asked to find the corresponding number delta. Given that epsilon is 0.3, find the corresponding number delta so that my y values are going to be within epsilon of L by keeping my x values within delta of c. All right, so here, this time, instead of just saying go up some positive distance, I have a concrete. I go up 0.3. The top of that interval would literally be the number 1.3. I'm allowed to go down 0.3, so the bottom number there would be 0.7. This picture's not drawn to scale. And I'm just looking for an interval on the x-axis that will keep my y values in there. And then I'm going to represent that with a number delta. All right, so what I'm going to do is I'm going to take this part from the definition of limit, and I'm going to work with it until maybe I learn about the x-axis. So f of x minus L is supposed to be less than epsilon, which this time is 0.3. I can look at my limit statement above, and my function f of x is the function 3x minus 2. My limiting value is the real number 1. All right, so in here I have 3x minus 3 is less than 0.3. And there's actually a sneaky way of going through this problem that's a little shorter than what I'm going to show you, but I want to show you the general way that'll work for most of the problems we see. So my next step is going to be to rewrite this absolute value inequality without the absolute value, which means 3x minus 3 has to be more than minus 0.3 and less than 0.3. So now I want to solve this inequality. All right, to solve that inequality, I'll simply do the same thing to all 3 pieces. Start by adding 3. All right, and now I need to divide everything by 3. All right, so I have an x in the middle. It needs to be less than 1.1, but more than, let's see, that would be 0.9. So what I know now is if I choose x's between 0.9 and 1.1, my y values will be within 0.7 and 1.3. Okay, that's not really what I was asked to do. I was asked to find a number delta. So what I have now is kind of the whole picture. Again, I'm probably not drawing this very well to scale. But what I have is my linear function that looks like this, and if I pick x's in this region, I get y's in the region I wanted to. All right, so we're not to scale, but that should work out nicely. Okay, well, epsilon was 0.3, and now I need to think about what the value of delta is. Well, epsilon is a positive distance here. Delta is supposed to be a positive distance on the x-axis. It's the distance I am away from 1. All right, well, the distance between 1 and 0.1, the distance between 1 and 1.1 is 0.1. The distance from 1 and 0.9 is also 0.1. So this tells me my positive distance delta is 0.1. And now I have a solution to that second problem. If epsilon's 0.3, my value of delta has to be 0.1. To keep the y values within 0.3 of the limit value of 1, I have to keep the x values within 0.1 of 1. We're going to see more examples like this in a minute. One thing I want to say here at the end of the problem is we've worked this problem to its conclusion, but this doesn't prove that this limit exists. For this limit to exist, we'd have to have a statement that says, for any value of epsilon that you ever give me, I would always be able to calculate a value of delta. All right. Well, that's it for now.